This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
We're now going to look at the second of the three forecasting techniques I mentioned, which are dealt with in chapter 10 of the free lecture notes. And what we're going to look at now is something called regression analysis. Which is doing the same sort of thing we were looking at with the high-low technique in the last lecture, but in a rather more accurate way. Because if you remember, when we did high-low, we were saying, if we've got a cost that varies perhaps with the production, in a perfect world, if we looked at the last several months and plotted them on the graph, in a perfect world, they'd all be precisely on a straight line. In the real world, I said nothing's perfect, and they may look reasonably linear, but some will be a bit higher, some will be a bit lower. And we wanted to find, the overall relationship. Now, the problem with high-low, if you remember, is it only looked at the two extremes and ignored what happened in between. What regression analysis does is it effectively tries to find the line that most nearly goes through all the points. And in fact, the way it does it, you don't have to prove the formula we use, but what it effectively does is it finds the line which minimizes the squares of the distances of the points away from the line. Some people call it the method of least squares. However, that's fairly irrelevant. We're trying to find the line that most nearly goes through it. But again, if you remember from when we did high-low analysis, I said that once we've got the value for the fixed and the variable costs, we could then use it for forecasting the total cost. I wrote up an equation last time, but if the total cost is always equal to the fixed costs plus the variable cost times the number of units. So if x is the number of units, it's x times the variable cost per unit. Now, before we got the fixed cost, the variable cost using the high-low method, with regression, we're still going to calculate the fixed cost and the variable cost per unit, but in a more efficient way. And you'll see on the page with section 4 on it, under regression analysis, we're after an equation y equals a plus bx. Where a is the fixed amount and b is the variable. And you've got two formulae there to calculate a and b. They look much worse than they actually are, but you're not given these formulae in the exam. I'm afraid you have to learn them. And as you can see, the formula for A is sigma y over n minus b sigma x over n. The formula for B looks awful, but n sigma xy minus sigma x times sigma y over n sigma x squared minus sigma x all squared. Now, it's better seen with numbers, and I'm about to, but sigma means sum of, as you're going to see. N is the number of pairs of observations. Now then, rather than talk through a formula blind, let's look at an exercise. On the next page, exercise 2, it's actually the same figures that we used in the high-low, but this time we're going to get the variable with the equation, but using these formulae, using regression analysis. It's fairly time-consuming. I'll try not to let it be too boring. Now, hopefully I'll get it right. But I'm going to set it up in various columns, as you see. So if you are doing it with me, leave space across the page. But first of all, in those formulae, we've got mention of x and y. Well, look at the formula. It says y equals a plus bx. And so y, a bit like I said when we did high-low, y is whatever depends on x, on the other variable. So here, because we're looking at total cost at different levels of output, surely the cost will depend on the level of output. And so the cost is going to be y, because it depends on the output, which is x. So I'm going to set up columns. I'll have a column for x and a column for y. X is the output, which is in units. Y is the cost, which is in dollars. And the first thing we do is simply list all the sets of observations. But I'm going to simplify it slightly here, because although the outputs are all given in units, and the costs here are all given in dollars, you'll see as we go through, because of the amounts involved, we've got to do various multiply them together and things. We're going to have lots and lots and lots and lots of zeros. It's going to get terribly messy. And so instead of writing the output down as 100, 400, 200, I'm going to simplify it. So it'll simplify our arithmetic, as you'll see. But I'm going to write it down in hundreds. So I'll do 1, 4, 2, 7, 6, 5, 3. So I'm going to treat my units as hundreds. It will make the arithmetic a bit quicker. And similarly, the cost, although the costs are 40,000, 65,000, just to avoid having too many zeros floating around and wasting time, I'm going to write them down in thousands. So it's 40, 65, 45, 85, 70, 70, and 50. So it doesn't really matter if you prefer to write down the exact figures, do. The only reason I've done this is, you'll see in a minute, it will make the numbers a bit more easy to deal with. Now let's start using the formulae. And if you look back at those formulae, keep the previous page in front of you. If you look back at the formulae, you'll see somewhere, well, in the formula for A, it's got sigma y, and later in the formula, sigma x. Well, sigma means sum of whatever comes after it. So sigma x is simply the total of all the x's. So if we add them up, 5, 7, 14, 20, 5, 7, 14, 20, 25, 28. That is sigma x, the sum of the x's. There's also floating around in the formula sigma y. Well, again, it's the sum of y, which, I've got my calculator, 40 plus 65 plus 45 plus 85, 70, 70, 50. The total is 425, sigma y. What else have we got? If you look in the formula for B, there's a sigma xy. Well, it's sum of whatever comes after it. It's sum of all the x times the y's. And so for each set of observations, let's work out x times y. So 1 times 40 is 40. 4 times 65 is 260. 2 times 45 is 90. 7 times 85 is 595. 6 times 70 is 420. 350. 150. So there's xy in each case. Sigma xy. Add them up. So it's time consuming, but it's just calculator work. 40, 260, 90, 595, 420, 350, 150. I get a total of 1905. So that's sigma xy. What else? Any other sigmas? We have sigma x, sigma y, sigma xy. The remaining one is sigma x squared. So again, it's the sum of what comes after it. It's the sum of all the x squareds. So let's square them all. 1 squared is 1, 4 squared is 16, 2 squared is 4, 7 is 49, 6 is 36, 5 is 25, 3 is 9. And so the total, or sigma x squared, is 4, 49, 36, 25, 9, 140. So we've now got everything we need, except n is also floating around in the formula. Well, I said before, n is the number of sets of observations, the number of pairs. And how many are there? 1, 2, 3, 4, 5, 6, 7. N is 7. So we've now got the figures we need, and we can now stick them in the formulae. But again, if you look at the two, we're trying to work out A and B. The formula for A, sigma y over n minus b sigma x over n, it's got B in it. So we have to work out B first, and then we can use our value for B to work out A. So let's work out B. B is n sigma xy minus sigma x sigma y divided by n sigma x squared minus sigma x all squared. So let's do it. N is 7. Sigma xy is 1905 minus sigma x is 28. Sigma y is 425 divided by n, which is 7, sigma x squared, which is 140, minus sigma x all squared. Sigma x was 28, 28 squared. Now, I don't know if you're efficient with your calculator, maybe you can do that all in one, but just for everybody's benefit, including mine, I'll do it step by step. The top bit's 7 times 1905 is 13335 minus 28 times 425, 11900 over 7 times 140, which is 980, minus 28 squared, 784. So I'm nearly there. 13335 minus 11900, 1435 over 980 minus 784, 196 is I get 73. I beg your pardon, 7.321. I'll talk about rounding shortly, but let's get it finished first. But 7.321. Having got B, we can now calculate A using the other formula. So A is sigma y over n minus B sigma x over n. Sigma y was 425. N is 7, the number of sets of observations. B, we've calculated, is 7.321 times sigma x, which was 28, again divided by 7, which comes to 425 divided by 7 is 60. Have I got my decimal right? Yes, 60.714 minus 7.321 times 28 divided by 7. 29.284 is 31.43. All right, so that's just calculator work, clearly. The question of speed. One thing here, though, to be very, very careful of. You see, we're after a formula, y, when y is the cost, equal to a plus bx, where x is the units. Now, I've got to be careful. You can write it now in two ways. The point being, when we did the costs were all in thousands, and so and the units, I beg your pardon, were all in hundreds. So that if I write the formula like this, A is 31.43, B was 7.321. That would give me the cost of the number of units, provided units were in hundreds. It would give me the costs in thousands. So A and B aren't the exact fixed costs and variable costs. We need to adjust. And because it's giving the cost in thousands, what we're going to have to do is this. To get the cost in total, it's 1,000 times all of those. So it's 1,000 times, that is 31,430. We're also going to have to multiply 7.321 by 1,000, because now we'll get the actual cost. So it's going to be 1,000 times 7.321. But because x was the units in hundreds, we multiply by 1,000, we divide by 100. So it's actually 73.21x. So be careful. Now, if that bit worries you, you can avoid it by, in the original table, having the exact figures. If you'd written 100, 400 and so on, and if you'd written 40,000, 65,000 and so on, then using the formulae, you would have come out with 7,321 for B and 31,430 for X. For A, I beg your pardon. But the other side of the problem, if you'd put them in hundreds, the whole amounts, 140,000 and so on, you're dealing with huge numbers. So you might like to make mistakes, so it's your choice. Hopefully, any questions you get will be smaller numbers anyway, so you won't need to do what I did. Anyway, there we are. There is our equation relating the cost to the number of units. And the 31,430, just as with high-low, that's the fixed cost. The 73 is the variable cost per unit. Now, I had used the same figures as we did with high-low. I can't look back because I've changed the screen. When we did high-low, we did get an answer a bit different. I have a feeling the variable cost was 75, not 73. But of course, they will be different. A I said from the very beginning, high-low only looks at the two extremes. This is a more accurate approach, a better approach. We've looked at all the values. And so I wouldn't expect to get exactly the same figures. And just as with high-low, we can now use it for forecasting. Look at exercise 3. It says calculate the estimated total cost if the forecast output level is expected to be 650 units. Well, no problem. Just like with high-low, stick it in the equation. The expected cost would be a fixed 31,430 plus variable 73.21 per unit times the number of units. It wants us to do it for 650. Which is what? Oh dear, 73.21 times 650 is 470. No, 47,587. 47,587. That gives me a total of 79,017. And is that reasonable? If you look at the original table, 600 actually cost 70,000. 700 cost 85,000. Well, for 650, well, it is somewhere in between. It doesn't prove it's correct, but it is somewhere in between. It does look reasonable. So there we are, beautiful. Except, although it's better than high-low, it's still not what you might call perfect. Because we've made one big assumption right from the beginning. We have assumed that the original points are more or less linear. I think here they probably are. If you put them on a graph, have a go yourself if you want, but you will find that although they're not exactly on a straight line, it is more or less a line, and we've found the equation of that line. But it could be the case that if we put them on a graph, maybe it looks something like this. Now that doesn't look anything like a straight line to me. It looks to me as though it's a curve. Whoops. And yet arithmetically, using the formula, we've just found the line that most nearly goes through them. We've found the line that most nearly goes through them is perhaps like this. You can use the formula on any set of values. But sure, there's only any point if they are more or less linear. If it was a curve, you couldn't be expected to deal with it in numbers. But if it was a curve and I was forecasting, you'd carry on forecasting around the curve. You wouldn't forecast as though it was a straight line. So that is one danger. We can work out A and B. We can come out with an equation of any set of values. But there's only any sense in it if they are nearly linear. That's 79,017. It's only really a valid estimate if, again, they genuinely are more or less linear. But how do we know, apart from drawing a graph, how do we know if they're linear? Well, there is a way of measuring the linearity without needing to draw a graph, and it's on the next page. It's something called the correlation coefficient. And there's a formula there. And I will actually use it because it won't take us too long. There's a formula there which looks awful, but fortunately you're not expected to learn it or use it in the exam. But the reason I am going to do it and talk through it is, although you will not be expected to calculate that figure, it says coefficient correlation R equals all of that, Although you won't have to calculate R, you are expected to know what the result means, what the relevance of it is. And so bear that in mind, please. It won't take me very long to calculate, to be honest. But you are not going to be required to do the calculation. The reason I've wound back to the table is if you look at that formula, most of the things in it we've got. We know what n is, we know what sigma xy is, sigma x, sigma y, sigma x squared. The one new term in it is sigma y squared. So I'm going to add one more column and get sigma y squared. And then I will use that formula. So be patient with me, please. Y squared 40 squared is 1600, 65 squared is 4225, 45 squared 2025, 85 squared 7225, 70 squared 4900, 50 squared 2500. So the total, or sigma y squared, is 27375. Well, I've got everything I need there. Let me clear some space, then we're not going up and down. Forgive me. Oh, won't be a second. That's better. Let's use the formula R. The top bit, it's n, which is 7 times sigma xy, which is 1905, minus sigma x, which is 28, times sigma y, which is 425, divided by the square root of 7 times sigma x squared, 140, 7 times 140, minus sigma x all squared, 28 squared, times 7 times sigma y squared, minus sigma y all squared. I'll try and be as fast as I can. Yet again, please, you are not required to use this formula or learn it. Anyway, the top bit I'll do all in one. It's 7 times 1905 minus 28 times 425. It's 1435. And it's positive. It will be important later. The top bit could be positive or negative, and it will matter, but it is positive. Divided by the square root of 7 times 140 minus 28 squared is 196 times 7 times 27375 minus 425 squared, 11,000, which is 1435 over 1468. And before anybody shouts, I know when you take a square root it can be plus or minus, but here the square root bit we always treat as being positive. So it's plus 1435 over 1468, and therefore R is plus point, if I keep to 2 decimal places, 98. Now, for the last time, you will not have to remember that formula. You won't have to calculate R. but you are expected to be able to interpret R. You could be given an R and expected to explain what it means, what the relevance is. And so what I'm about to say is what's important. Firstly, I can't prove this to you, you have to trust me, but the value for R will always be between +1 and -1. It has to be. It's always between +1 and -1, the way the arithmetic works. Here we've got +0.98. It could be +0.7, it could be -0.2, and so on. And secondly, if it's +1, it means we've got perfect positive correlation and what that means is perfect, it would mean the points lay exactly on a straight line, and it would be like we've been looking at, it'd be a straight line going up. So here, when we were looking at cost as against units, more units you expect more cost. Well, if it was perfect correlation, the points would be exactly on a straight line going up. On the other hand, if you were at the other extreme and you've got -1, we say with perfect negative correlation, and that would mean it's not going to relate to costs for in a second fairly obvious reasons, but it would mean if you put the points on a graph, but again they'd lie exactly on a straight line, but a straight line sloping downwards. I'll give you an example of that in a minute, but where one variable goes up, the other variable goes down. If we're in the middle, if we get R equals 0, that would mean there was, sorry, I'm doing the graph first. That would mean there's no correlation at all. So if we drew them on a graph, the points are just sort of almost at random. There's no link between the two variables. So the best is a coefficient of correlation of 1. If the coefficient of correlation is 1, they're exactly linear, and I'm going to be pretty confident in my forecasts. The further away it is from 1, the more they're not on a straight line. And the further away it is, the more worried I'd be about a forecast. For our example, it was what, 0.98. So it is pretty close. So although they're not exactly linear, I wouldn't claim my forecast is perfect, but they are fairly close, so I will be reasonably confident. Just to make sure you've got it, look at exercise 4. Our techniques can be applied to scenarios outside management accounting. We can use this on any two variables. You know, the number of cigarettes you smoke and the number of times you fall ill, that sort of thing. But it says here, state what type of correlation you would expect to find in examples below, positive, negative, or no. A, the number of hours spent studying and the likely exam score, the mark in the exam. Well, would you not expect that the more you studied, the higher mark you got? And so you'd expect, not necessarily perfect, but you'd expect positive correlation. Hours of study, more hours of study, a better mark. Again, I'm not claiming it to be perfect, but you would expect them both to work together. B, number of pages printed and the ink levels in a printer. Well, surely the more you print, the less ink you'll have left. And so I would expect it to be negative correlation. The amount of ink, the number of pages. Again, I wouldn't claim it's perfectly linear, but you would expect the correlation to be negative. And finally, well, of course, you can guess what's coming with C. The shoe size and the level of disposable income. I can't, maybe somebody can think of a connection. I can't think of any connection at all between them. I wouldn't expect the shoe size to have any relationship at all with the level of income. And that if we did have a graph, different shoe sizes, income could be anything, they'd be all over the place, no correlation. I'd expect it to be 0 or close to 0. Finally on this, it says problems with regression analysis. Well, I've already said why this is an improvement on high-low. We're not just looking at extremes, we're looking at all the values. The problems are, well, one is similar to high-low, that there's a risk if forecasting outside the range. You see, even if they're very linear over the range we've looked at, if you started forecasting for, the highest here was 700 units, if you started forecasting for 1,500 units, well, just because it's linear for our observations doesn't mean it would carry on being linear outside the range. So there's a danger. A second danger is how many of observations we've looked at. I'll write it down and then explain why. The number of observations considered what I'm getting at here, you see, if we'd only looked at 2 observations, those lie exactly on a straight line. It's perfectly linear. But you're not going to tell me that because it's perfectly linear, oh, any forecast is going to be perfect. Good heavens, it could be that there was actually some sort of curve. Daft. We've only looked at 7 observations. It seems to be reasonably linear. But the more observations you've looked at, the more past months you've looked at. If it's still more or less linear, you're going to be much, much more confident of any estimations, any forecasts. Okay, so that's regression. So we've done 2 of the techniques now. Two of the techniques now. High-low method, regression. Both looking at the same sort of thing, but the regression more complicated but more accurate. The third one, which we'll look at in the next lecture, is rather different, even though it's still connected with forecasting, but it's time series analysis. But I'll look at that in the next lecture.